Okay, let's go ahead and get started. We're not going to spend much time on the computer today. I'm going to do a little, just at the beginning, I'll show you the question of the day, and then we'll come back to this for a little something at the end. So this was, of course, the answer is int. Why wouldn't int be people's favorite? Anyway, in any event, that was an interesting question to ask. Today, we're going to spend most of our time on the document camera. So let me try to bring that up, and let's see if I can be watching the same thing that you're watching. Let me try to turn this a little bit so it's a little easier for me to write. We're going to be talking about what are known as linked lists. I've been mentioning this for a little while now, that this is something we were going to be covering. We're going to cover it all this week. There will be 3 different sections where we talk about linked lists, tomorrow, Thursday, and Tuesday of next week. And then there'll be a linked list homework assignment for you to work on. This is one of those topics that I think you will find that 143 students tend to have a strong emotional reaction to. So you could try an experiment. Find some friends of yours who you know have taken 143 already, and just try catching them at an offhand moment and try just kind of saying linked lists and see how they react. You might very well see them wince, or whatever. Anyway, they are likely to have some kind of a strong reaction. People tend to have emotional responses to linked lists. Well, let me describe it in this way. I'm going to have a question on the final for linked lists that is worth 20 points. And the average score that I get in quarters in which we do proctored graded exams is around 10 out of 20. And overall for the exam, I tend to get an average of maybe 75. So 10 of the 25 points that people lose on average on the final, they lose on this linked list question at the end of the quarter. So there are clearly people who struggle with linked lists. I think that studying linked lists is important, and I think that it gives you good practice, but I'm just kind of warning you in advance that this is a substantial topic. In your case, you'll have to use it for the homework, but your exam is not going to be graded in the same way it is during normal quarters, so that will be less of a concern for you. I wanted to say a little bit, before we get to talking about the linked lists themselves, we've been talking about arrays, and I wanted to draw a contrast between arrays and linked lists. So let me try drawing an array with 1, 2, 3, 4, lots of space here, 6 different elements in it. And suppose that it had the values 0, 2, 40. I'm looking at my notes here to make sure that I'll match what I have, what I put into the notes for today. And obviously we have an indexing scheme, 0, 1, 2, 3, 4, 5, different indexes, up to 5, for these 6 different values that are stored in the array. We've been drawing pictures like this, and in case it wasn't clear, it's worth pointing out that the way that arrays are stored in memory is as a contiguous block of memory. So there's no gaps in here. However much space you need for the array, you do set aside that block of space. Well, there are things that arrays are good at, where linked lists are not so good. And it's kind of funny. There's this complementary nature where the things that arrays are good at, linked lists are bad at, and the things that arrays are bad at, linked lists tend to be good at. So there's a kind of an interesting contrast there between them. One of the things that's good about arrays is that we know that we can have what's known as random access. So you know that all of these different values are stored right next to each other in memory. You know how much space each one takes up in memory. So even if there were 1 million of these things, if you wanted to get to, say, the 5,000th element of them, you know exactly where that would be stored in memory, because they're all the same size and they're all right next to each other. So you could very quickly jump to element 5,000 of the structure. So that's something that arrays are good at. What arrays aren't so good at, we've seen, is things like, what if you wanted to insert something at the front of the array? Then you have to shift everything over. And if it was an array like this where everything is filled up, then it's hard to add something. It's hard to make an array bigger or to make an array smaller. What we saw that the array int list does is that it makes a brand new array, and then it copies things over. So arrays aren't very flexible in that sense, in terms of inserting and removing in the middle of the structure, that you might have to shift things, and changing the size of the structure is something that it doesn't do very well. But random access is great. Well, the other approach to this would be to say, well, let's not worry about where these things are stored in memory. So maybe I have a 23 here, and a 2 here, and a 40, and a 0, and a 14, and the 72. And I've made these things look like they're next to each other, but I'm actually assuming there could be a whole lot of stuff in between here. Maybe, maybe not. I mean, these are just kind of at various random kinds of locations in memory. And if you wanted to store a sequence like this, know that it starts with a 0, you'd have to have some way of remembering that that's the starting point, that we start at this value 0. What comes after the 0 is a 2, so you'd have some kind of a link. This is the linked list idea. We have something that links this one to say that the 2 comes next, and then 40 is going to come next, so we'd have a link that kind of goes from the 2 to the 40. After that comes the 23, so we'd have kind of a link that goes like that. After the 23, we have 14, which is way over here. So we'd have some kind of a link that looks like that. After the 14 comes the 72, so we'd have some kind of a link like this. And the 72 is the end. There's nothing more. So you can imagine that we have some kind of special value here that could be called a terminator or something that indicates no more. That's where this thing ends. So we store these we're going to do this with references, that we store references to things, and that allows us to have the flexibility of having things stored anywhere in memory. Now, if they're stored anywhere in memory, then we're not going to get random access. If we want to get to the 5,000th element, we have no clue where it's stored. There's no pattern for us to follow. So the choice for us is going to be to start at the beginning and go next, 5,000 times until we get there. So this is what's known as sequential access. Files have sequential access, that you start at the beginning of a file. We saw this in the 142 class, that you read the file from the beginning and kind of go to the next. When I was younger, we used to have cassette tapes that we used that had sequential access to them. So if you had a tape, you wanted to get, say, to the 6th song on the tape, and you were at the beginning of the tape, you'd have to hit this button labeled fast forward, and it would go ka-ching, 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 ka-ching. You keep it pressed for a while, and you hit play, and you find that, I went too far. I went to the 8th song instead of the 6th song. So you hit this other button called rewind, ka-ching, 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 to kind of go back. So you have to get kind of positioned to just the right spot. And it could take a long time, to get something that's late in the tape, for example. There's a lot of fast forwarding to do. So that's not true with the array. With the array, we can jump around very quickly. So sequential access is the slow thing, and that's what we get with linked lists. Random access we get with the arrays. This would be like a CD player where, the CDs allow you to jump, from one to another. In fact, an interesting thing about CD players that you never saw on a cassette player. I mean, people actually used to use cassette players to play music for themselves. And when we had CDs, people would have CD players. And the CD players have a little randomize button, that you can get the songs in a random order. Okay, so arrays are better in that sense that they give you random access. The linked lists give you sequential access, which is not so good. But suppose you wanted to insert something at the front of a linked list. Remember, inserting at the front of the array, we had to shift everything over to make space for it. Here, we just rearrange our links. So we could have something else be at the front, and we'd point to it, and then it, in turn, could point to the 0. So we rearrange the links within memory, and we have something at the front of the list. In fact, then it would have one extra value in it that it didn't have before. I mean, we can grow and shrink the list just by creating new links. And if we wanted to say, add something at the end, this, by the way, would also, that was kind of, if you wanted to remove at the front, the same thing would be true, that we'd have to shift everything over. If you wanted to add something at the end, well, if the structure is full, it's hard to add to the end. Here, it's very easy to add to the end because, again, we just rearrange links. Instead of having this go to a terminator, it could go to some other value, which then is followed by a terminator. So linked lists are much more flexible in terms of rearranging links, and so that means changing the structure. So inserting and removing anywhere within the structure, making it bigger, making it smaller, those are all easy things to do with a linked list, not so easy to do with an array. So as I said, things that the one is good at, the other one is not so good at, and vice versa. I thought you might find it interesting. I had a quote from a fellow named Tony Hoare. References are like jumps leading wildly from one part of a data structure to another. Their introduction into high-level languages has been a step backward from which we may never recover. So he is not a fan of this kind of approach. Tony Hoare does not like the idea of creating a data structure using references. He's a famous computer scientist. He's famous for having come up with the algorithm known as quicksort, which is probably the most commonly used sorting routine in the world. So anyway, Tony Hoare, not a fan. I thought you might find that interesting. All right, well, I did want to mention a couple more ideas. One of the things that we are going to be exploring in all of this is exploring the difference between data and a reference to data. So that's kind of one of the things that makes linked lists challenging, is understanding this distinction. One of the ways I like to think of for this is I imagine something like, suppose we took somebody from the past, like Ben Franklin. We brought him forward into the future, and we showed him these fancy new devices called cell phones. So he sees you on your cell phone talking to your mother, and he's like, how is that possible? You're using that little box to talk to your mother. How does that work? Is your mother inside the box? Well, Ben probably wouldn't say that. He'd be smart enough to know that's not true. But, and can you talk to other people besides just your mother using that box? Yeah, you might say that, I've got information for 50 different people. 50 people are inside that little box? Isn't it heavy? 50 people would, it's the joke. Ben wouldn't be stupid enough to say that, but I'm imagining, that if you had the actual people, that's like the actual data in the phone, then the phone would be big and bulky and heavy, and you'd be carrying around 50 people. But you don't have 50 people in your phone. You have 50 references to people. You have 50 phone numbers, which keep track of a reference to people. So we're going to be talking about this idea of references a lot. I've mentioned this before, but it's worth kind of repeating it here, is that we have these different analogies for what a reference is. So one analogy is to just draw pictures so that, you can just kind of have a little arrow that points at something. So an arrow is a way of understanding what a reference is. And I've known some computer science instructors who think that we shouldn't be talking about references as anything other than an arrow. That's kind of the right way to do it. I think that might be people who are a little more visually oriented. But there are some people like thinking about pictures, and so that can be helpful. So if you think of a reference as being an arrow, that's not a bad way of thinking about it. In languages like C and C++, they have what are known as pointers, and pointers are references. When Java came out, the designers of the language, wanted to distinguish it from C and C++, and they were very dismissive of the way things are done in C and C++. And so they said Java has no pointers. They kind of wanted to make a distinction like that. And people said, well, if it has no pointers, then how come null pointer exception is the most common error that we seem to get in our programs? So they had to say, well, really the right way of thinking of it is that it's all references, it's all pointers, and if it's all pointers, it's no pointers. Anyway, if you know what a pointer is, then you know what a reference is, because it's basically the same idea. In C and C++, they tend to think of this as being a memory location and an address. And that's not a bad way of thinking of what a reference is. You could you could imagine that what you're keeping track of is the location of where this other data is stored. So that could be something that you're storing is a location where data is stored. That's a way of keeping track of a reference. Another way of thinking about it that I've been using a lot is that it's like a phone number with a cell phone. And what I like about that analogy, one of the things I like about it, is that the people who popularized object-oriented programming like to think of the idea of passing messages between objects. So different objects that are kind of talking to each other is the way that they like to think about what's going on with the programming. All right, let me make sure I'm going to be doing the right thing here. Okay, so I wanted to show you a little picture of the basic building block for linked lists. Kind of reminds me of if you were to try to describe Lego to somebody, if you showed them just one Lego building block, I think they'd find that kind of not very interesting. But if you show them kind of a structure that you built out of it, they'd say, well, that's a little more interesting. Well, so the basic building block is something that has a place to store some data and a place to store a link to the next thing. So that you might store something like an 18, and you might store a reference, a link to the next thing. This little item, this little object here, is something that we're going to refer to as a node. So linked lists are composed of nodes. You construct one node for each bit of data that you want to store, and then you link them together. That's going to be the basic idea. We're going to need to have some kind of a Java class for storing this. So we want to have a public class that I'm going to call listNode, and it's going to have two things in it. Now, I told you that in general we want all fields to be declared private. This is the one exception, is in node classes. I'm going to talk about this a little more next time, why it's okay to do what I'm about to do, but I'm going to make public fields. So I'm going to have a public int field called data. So just like we did array int list, we're going to do linked int list. We're interested in understanding the built-in structure linked list of E, where E can be filled in with different kinds of things, but for our purposes, we're going to fill it in with int. We're going to be looking at a list that stores simple ints. Again, it's to be able to focus on the issues of the structure and how to manipulate it and how to write code for it. Before we're done, we'll see how you could turn our a linked int list into linked list of E. So we don't want to have to deal with the complexity of the generic type while we're learning how to use it, but eventually we'll see how to do that. We also want to have a public field that is going to store next. And so the question is, what should its type be? What should we fill in here? But we're going to want to have something that looks like this. Every list node has two things in it. So what should we be storing here? We want to store an arrow, a pointer, an address, a phone number, a reference to the next node in the sequence. And it turns out that what we're going to want to put here is list node. So this is an example of a class where the name of the class is list node, and we use list node inside of the class. So we have a field of type list node. So we're using the name of the class inside of the class. The name recurs, and so we would refer to this as a recursive data structure. This is the first example we've seen of a recursive data structure. We're going to talk more about recursion later, but I thought I'd point out that that is so, that this has this funny relationship. Now this is, right away we're getting into a situation where it's really important to understand the difference between data and a reference to data, because you have to think about, well, what is this thing called next? And if you think that this thing called next is a list node, is an actual list node, then what you're saying is that what's in this box is a complete node. So in other words, if we pried open a list node, we'd find that there's a list node inside. And then if we pried that one open, we'd find that there's a list node inside of that. And if we pried that open, we'd find there's a list node inside of that. It would be like those Russian dolls where you keep opening them up and there's a smaller one inside. Except the Russian dolls end at some point. And this would be something that would have no end to it. So it's really important to understand that what this is not an actual list node, but a reference to a list node. So again, if you think of it as an arrow, that's not a bad way of thinking about it, or any of these other ways of thinking about it. It's a reference to the next node in the sequence. That's what we're storing instead. All right, well, what I want to do is I want us to explore this a little bit by writing some code that would construct a list that would store 3, 7, 12. So I want to store 3 pieces of information. That means I'm going to end up constructing 3 different nodes because each bit of information is stored in one node. Let me do that. Let me start here by saying list node list. So let me introduce a variable called list. And I'm going to draw a picture here of kind of what I have at different points in time. So when I declare this variable, I have a space set aside where I can store a reference to a list node. So one of the questions I like to ask the class when there's people here, but you aren't here, so I'll just have to kind of ask it to myself and answer it, is do we have any nodes yet? And the answer is no. List is not itself a node. It's a place that can store a reference to a node. We don't have a node until we call new. So what we would say is list is assigned to a new list node. Now, there's going to be a lot of tricky things that come up in constructing various node objects and putting them together in a list. And so I'm going to encourage you, whenever you're dealing with assignment, to be looking at the right-hand side first and then thinking about, about the left-hand side. So the right-hand side here says to make a new list node. So what does that do? That makes a new node object. Now, the way that I normally do the node object is I just kind of have a box that has a place to put some data and a place to put some a next link. And it's kind of understood that it's data here and next here. But for this first example, let me actually be a little more explicit and say that that's where we're storing data and that's where we're storing next. So when you ask Java to make a new list node, it goes out, it constructs the node, and it returns a reference to that node. And what are we doing with the reference that's being returned by that? We're storing it in list. So the arrow, the memory address, the phone number, however you want to think of it, is going to be stored in list, which means that it points at this node that we just constructed. We've seen that you can go inside of a node by inside of an object by using the dot notation. So you could say list dot, and then that's a way of kind of going into this node to refer to its individual fields. The dot is known as the dereferencing operator. It's the operator that follows a reference, it follows an arrow, and goes into an object. It's the one also, by the way, that can throw a null pointer exception. If you end up saying null dot, then that's going to throw a null pointer exception. We'll talk about that more in Wednesday's lecture. So which field am I interested in? Well, I want to put a 3 inside of here. So in list.data, I want to store a 3. So let me put that right there. And I do want to do something with list.next. What is it that I want to do with list.next? I want to set it to be a new list node. So again, look at the right-hand side. You're asking Java to go out and make a brand new node. So it does that. It makes a brand new node that's got a place to store some data and a place to store a next. And so it returns a reference to this object right here, an arrow that points at this object right here, or a memory address or a phone number. And what do you want to do with that reference? You want to store it in list.next. List.next. You want to store it in this box right here. This box is list.next. So that's where we store the arrow that comes back from the call on new. How do we set this to be a 7? Well, we've got a variable called list. It's our only variable. So we need to kind of start with list. It stores a reference, so we dereference it with a dot. Which field am I interested in between these two? Well, I'm going to want to set a data field, but it's not this data field that I want to set. So the field I'm interested in initially is list.next. So list.next is this box right here, and it stores a reference, it stores an arrow, so I can dereference it with a dot. List.next dot is the way of going inside of this right here. And which field am I interested in here? I'm interested in the data field. List.next.data, I want to set to be a 7. So that puts a 7 right here. And I do want to do something with list.next.next as well. So that's the other field that's inside of this object, this one right here. And what do we want to do with list.next.next? We want to set it to be a new list node. This is our third call on new to construct a third node. And again, look at the right-hand side first. It says to make a node. So Java goes out and it makes a node for you that's got a place to store some data and a place to store some a next. So that's kind of what the right-hand side said, is to make a new list node. And where do we want that reference to go? In list.next.next. List.next.next. This box is known as list.next.next. That's where I want to store the arrow to the thing that was just constructed. So we store an arrow to this right here. So I'm trying to get 3, 7, 12. So how do I get a 12 inside of here? Again, my only variable is list. Which of the fields am I interested in this first node? I use the dot to get inside the first node, and it's the next field that I'm interested in that node. That stores a reference, so I use a dot to get inside of the second node. What field am I interested in here? Not its data field. I'm interested in its next field. And that also stores an arrow, so I can use a dot to dereference that and get inside of this node right here. And here, the data field of this, I want to set to be 12. So I'll put a 12 right there. And then what about this right here? That's list.next.next.next. That's list.next.next.next. Now, it turns out that when we call new, remember that that's a field. And Java will set the fields of an object to the 0 equivalent for the type, which would be null in the case of an object like list node. So this kind of was set to null automatically by the constructor, but it's not a bad idea to go ahead and kind of be specific about that we want that to be set to null. So this is, it's not necessary because that's what the constructor will do, but it's not a bad idea to be explicit. And the way that we usually draw that in the linked list case is by putting a slash through that box. So that kind of indicates that that has a null value. So that's how we build up this list that's got 3, 7, and 12 in it. At this point, I usually get somebody who asks a question along the lines of, do you always have to write linked list code in this tedious way? And I'll try to make the joke, yes, of course. If you have 1 million customers, you have to have 1 million .next. Anyway, it's a stupid joke. No. Obviously, this is not how we're going to want to be manipulating linked lists, especially as they become large. So we're going to want to write more general code. We're going to want to write loop-based code. But I found that linked lists are challenging enough that I like to develop it in stages. So what we're going to do first is we're going to talk about problems like this, where there's no loop involved. There's just kind of a small, what I call a neighborhood problem. A small number of nodes where you really can write code like this, where you're setting individual links. Because basically what you're going to find with linked list code is that you need to be both of these skills. You need to be able to do the neighborhood type work, but you also need to be able to incorporate that into a loop. So we're going to need both. But so before we get to the confusion of doing loops, we want to practice neighborhood problems. That'll be tomorrow's section, is practicing the neighborhood problems. And then we'll do loops on Wednesday, and then we do kind of more complicated loops in Friday's lecture. And the sections follow that same pattern. So tomorrow will be neighborhood problems in section. Thursday will be somewhat simpler loops, and then next Tuesday will be the more complicated loops. Well, let me draw this picture again where I've got list, and it's pointing at a node that's got a 3 in it, and it's pointing at the node that has the 7 in it, and it's pointing at the node that has the 12 in it. As I said, I don't normally label these with the data and next. I normally just kind of draw it in that way. I wanted to talk about two specific things, just to talk about what would happen. So what would happen if I said list.next is assigned to null? So I want to think about that line of code. And, before I do that even, let me just kind of, point out that it's worth, reminding yourself about the different possibilities here. List is a variable that points at this first node. List.next is this box right here that's storing a reference to the second node. That's list.next. List.next.next is this box right here that's storing a reference to the third node. And list.tripleNext, list.next.next.next, is this box right here that currently stores a null. So now what happens when I say list.next is assigned to null? List.next is this box right here. And so if I set it to null, that would be setting this to be a slash. So kind of this is now storing a null value. I haven't drawn that picture very clearly, but I think you can use your imagination and understand that that's kind of a node now that is terminated. It's got a null here instead of storing an arrow to these other things. So the question is, what happens to these two nodes over here? This is kind of truncating the list. This is chopping off the last two elements of the list and turning this into a one-element list. Well, there's lots of analogies that people use for this. One of the more common ones is to think of each of these nodes, each object in a program, as being like a helium balloon that can float away. And then the reference to it is kind of like having a string, that you keep track of it by holding onto a string. So what we had before was list was a string that connected to the first balloon, and the first balloon had a string that connected it to the second balloon, and the second balloon had a string that connected it to the third balloon. So what I've done here is I've disconnected that first balloon from the other two, and what happens to the two balloons? They float away. They kind of float to the ceiling. That's not a bad way of imagining what happens. Now, in some programming languages, that's a problem. In fact, you might wonder, in C and C++, you're not allowed to do that. You're not allowed to just let the memory go away, because over time you start running out of memory. You might wonder, why is it that sometimes when I go out of a program and restart it, it suddenly works again? Well, that's, a program with a memory leak is one that will have that observed behavior, that kind of restarting the program fixes something. Java's different. In Java, these things will just kind of sit there in the ceiling, and Java will reclaim that space if it needs it. There's a process known as the garbage collector that will kind of come into play whenever you need it in order to be able to reclaim the space if you need it. So you don't have to worry about that. Java will worry about it. Now, it could be that you don't want to lose this data. So that's one of the things that makes linked list coding a little trickier, is that that you have to be careful. If you let go of the helium balloon too soon, it floats away and you've lost track of some data that you actually needed. Let me mention another one of these. What if list, we go back to what we had, lists or this, the 3 pointing at the node with the 7, pointing at the node with the 12. What would happen if we said list is assigned to list.next. So what if I executed that line of code? So list.next is this arrow right here. What if I set list to be this? So I'm copying this arrow over to here. So now what's stored in list is something that points over to here. So the node is still pointing over there, but now list is pointing over there. That turns list into a 2-element list. Now 7 is at the front of the list. Basically, this line of code removed what was at the front. And since nothing is keeping track of this node with a 3 in it anymore, nobody has a reference to it anymore, it floats away. It's a helium balloon that floats away. So we would have lost access to it. It doesn't matter that it's got a pointer into some things that we're retaining. It itself, it's unreachable. And so therefore, the garbage collector would reclaim that space if it needed to. Okay, I wanted to show you one more thing, and then we'll talk about a couple of extra issues. So this is the list node class. I'm going to post this on the calendar for today. So there are the 2 fields that I mentioned, but it's going to have some constructors. So it kind of has one, real constructor that does all of the work, that's got a data and a next, that it sets. And so that's the constructor that does the real work. And in the other 2 cases, I'm using this notation, this with parentheses, which I had pointed out was one constructor calling another constructor. So this is the 1 argument constructor calling the 2 argument constructor. This is the 0 argument constructor calling the 2 argument constructor. And so if they don't specify what next is, we'll assume it's null. And if they don't specify what the data is, we'll assume that it's 0. So that's kind of nice that now with constructors, we can make that list with the 3, 7, 12, we can do it all in one line of code by using the constructor. So I wanted to mention that. And then what I want to do in this last little part of the lecture then is I want to talk about what we're going to be doing in section, and this will also be on the exam. So I have before pictures, and oops, I didn't mean to do that, sorry, and after pictures. So the before picture I want to draw here is, suppose that I have a variable p that refers to a node that has, what did I want, a 2 in it, which refers to a node that has a 4 in it, and then there's a null that terminates that list. And we've got a variable q that stores a reference to a node that has a 3 in it, and it in turn stores a reference to a node that has a 9 in it, and then there's a terminator for that. So two element lists that are using the variables p and q to refer to them. So that's the before picture, and then suppose that the after picture then, the situation that I want you to get to is that we want to have P referring to the node with the 2 in it, which in turn is referring to the node with the 4 in it, which in turn is referring to the node with the 3 in it. And we want Q to be referring to the node that has 9 in it. So the challenge is for you to write code that turns the before picture into the after picture. So this is an example of a little neighborhood problem. And so this is an example of something that I find is helpful for students to practice before we get to trying to do the full implementation of the linked lists. So, okay. I think that initially people are a little stuck, on how do we approach a problem like this. So something that I think is a useful thing to think about is how many different places are there here where I can store a reference to a list node? So this is, again, a great question to ask the class because I get different kinds of answers. How many places do you see in this before picture where I can store a reference to a list node? And some people say 2 because there are variables called P and Q. that store references to list nodes. There's 2 variables, so an answer could be 2. Other people say, no, it's the nodes that matter, the actual objects. And there are 4 objects here, and so there are 4, and each of those objects has a next field where it can store a link to the next thing. And so they say there's 4 places here to store a reference to a list node because of the 4 objects. Well, really, they're both right. So the right way to kind of think about it is that there are 6 places here where we can store a reference to a list node. I'm a little torn about kind of how to refer to this variable q and this variable q, the variable p and this variable q. I draw a little box that's meant to kind of distinguish it from a node, so that you know that it's not a node. But I do actually make it a box. Some people like to make it an arrow, to kind of make it clear that it's different than an object, that a variable that stores a reference is different from an object. And you'll see that's the way JGrasp draws the picture too, is they don't draw the little boxes that I draw. But so let me go ahead and number these. They're 1, 2, 3, 4, 5, 6. So I would say that there are 6 different places where we can store a reference to a list node. So one of the ways to approach a problem like this is a very mechanical way. And in fact, if you're working on these problems in section tomorrow and you're trying to help each other or discuss it in a group, this is a helpful way to kind of approach it, because what you can do then is kind of write down which of these numbered boxes is going to change. And it's a mechanical thing. Just compare what's here with what's here and tell me which of these boxes are different. So I normally ask the class to tell me a box that's different, and I kind of often get them in a slightly different order from people. But notice this box 3. This is the node that has a 4 in it. Here it's storing the value null. Here it's storing a link to a node. So that box 3 is going to change. That's one of the ones that we're going to change. How about this box 4? Box 4 is the value of the variable q, which here is storing a reference to the node with the 3 in it. Here, q is storing a reference to the node with the 9 in it. So box 4 has to change as well. And notice this box 5 here stores a reference to the node with a 9 in it. That's the node with 3. And down here, the node with 3 in it stores a null. So that box 5 changes as well. So boxes 3, 4, and 5 have to be changed. The other ones do not. The other ones you'll find, match what they were in the before picture. So what you know is that at a minimum, there are going to be 3 lines of code in the solution, because you're going to be changing at least 3 different things. There might be more. So one of the things that you often do in writing linked list code is you often introduce an extra variable to keep track of one of these references. We often refer to it as a temp variable. In fact, we often use a name like temp. So you could have list node temp equals and set it to one of these different values. Well, it's like those helium balloons. You want to make sure that you don't lose track of them. So by setting up a variable temp, it's a way of saying, well, let temp hold on to that helium balloon, because then I can go around and rearrange things and I won't lose the balloon. So I won't lose track of it. And you are certainly allowed to introduce temp variables. So don't be shy about using a temp variable to solve a problem like this. This particular one we can solve without a temp variable, and I'm going to do it that way. But it's perfectly fine to be using temp variables if that makes it easier for you to solve the problem. What I would say about these 3 things, the 3, 4, 5, is that between these different boxes, which one is storing a value that is not that important? And the answer is it's this box that's got the 3 in it. It's storing a null. So we can change it without losing track of any of our helium balloons. Well, how do we refer to this box right here? That's p.next. That's how we refer to that box right there, p.next. And what do we want to set it to be? We want it to point to the node that has the 3 in it. Well, where is that arrow? Where's the arrow that points at the 3? That's q. So we want to set p.next to be q. So what that will do is that will change this link so that it points over here. So it now points at the node that has the q in it. Now that it is pointing at the node with the q in it, it's kind of keeping track. Excuse me, I did that the wrong way. This is pointing at the same thing that Q is pointing at. In fact, I did it exactly the wrong way. It points at the same thing that Q points at. So it doesn't point at Q. It points at the node with the 3 in it. Sorry about that confusion. So the arrow that's pointing at the node with the 3 in it gets copied here. So it's an arrow that points at the node with the 3 in it. Once we do that, then it's keeping track of the node with the 3 in it, which means we're able to change the value of Q. We can set Q to something different because it doesn't need to keep track of this node with the 3 in it anymore, because that's this link here. Well, what do we want to set Q to? We want Q to be pointing at the node with the 9 in it. Well, where's that arrow? That's this one right here, which is Q.next. Well, we wrote that line of code on the piece of paper that I had before. This is the way to kind of reassign a list so that it skips the first thing. So that Q gets reassigned so that it points at the node with the 9 in it. So Q gets set to what's in Q.next. And so now that we've kind of done that thing, we want to change this node that has the 5 in it. Q is now pointing at that helium balloon that's got the 9. So now we're able to change that box that's numbered 5. How do we get to that? Well, that used to be Q.next, but it's not Q.next anymore because Q has changed. So we can't refer to this as Q.next. How do we refer to it? That's P.next. That's P.next. And what do we want to set it to be? We want that to be set to a null. We don't want it to be pointing at a node. So we'll set it to be a null. So those are the 3 lines of code that I would propose. I want to show you something on JGrasp. So let me come back over to the laptop. Oops, I've got the wrong thing here. Let's send this to the projector. Okay, that's what I wanted. And let me come into JGrasp. So what I've done in JGrasp is I've set up a little program here. I've set up a thing called dummy. I don't really, a dummy variable. I don't really want to observe dummy. I want to observe P and Q. This is kind of the way to do it so that it works well in JGrasp. It sets up this variable called dummy, and then it sets up P and Q. If you observe dummy, so I'm going to drag this out. So again, it's not dummy that I want to be observing. I want to observe P and Q. But when it sets up that dummy variable, it also sets up these 2 variables P and Q. It shows you all other things that are sitting there. So there's kind of this list that P is keeping track of, and this 2-element list that Q is keeping track of. So let's watch it here. I think it'll be a little easier to see in JGrasp. So the first thing we do is we set P.next to be Q. So this is P. Oh, I guess actually it does have the little box, doesn't it? It's funny how over time James Cross has been changing JGrasp so that it looks more and more like the pictures in my textbook. So now he's drawing it exactly the same way that I do too. A little box instead of a big box. P is pointing at the node with the 2 in it. So that's P.next, and that's P.next. So I'm changing P.next. This box right here, I want to have this be set to what Q is. Well, Q is storing a reference to this node with the 3 in it. So this box is going to point at the node with the 3 in it. So let me let that line of code execute. And it scooches this up here so that you can see there's that link pointing at the node with the 3 in it. Q is still pointing at it too. They're both pointing at it. Now I set Q to be Q.next. Well, Q is pointing at the node with the 3 in it. Q.next is this arrow right here that's pointing at the 9. So I'm resetting Q to point over at the 9 instead of pointing at the 3. So as that line of code executes, we set that Q to Q.next. And now we want to break this link right here. This is supposed to be set to null. Again, we can't refer to that as Q.next anymore because Q has moved. But we can refer to it as P.next when we want to set it to null. So it does that, and now we have our after picture, and it matches exactly what we saw before. JGrasp is going to be very helpful with linked list debugging because it draws great pictures of linked lists. We'll do more next time when we'll be talking about loops, and you'll be practicing the neighborhood stuff in section. Section tomorrow will be very important for you to do. So I'll see you on Wednesday.